Assalamu alaikum. My name is Zoha Naeem, roll number 21TE01 from Telecommunication Engineering Department, UET TAXILA. Today I will be discussing lab number 3 of digital signal processing. The title of this lab is plotting unit impulse, unit step, exponentials and making out signals using deltas. Moving on to task 1, we are required to create a function that can generate an impulse sequence. For this, we have the function impulse sequence that takes three input arguments named n0, n1, and n2. The next two lines generate the impulse sequence. It creates a sequence of indices from indices n from n1 to n2, then sets x to 1 where n equals n0 and 0 otherwise. Now, this code shifts the unit impulse towards right and left by modifying the n0 argument accordingly. It also demonstrates the scaling of input sequence by multiplying it with a scalar value. And the script plots the original and modified signals using a stem command. Here's the output of the function. For task 2, we are required to create a unit step function. Here we have step sequence function which takes three input arguments n0, n1 and n2. This line defines a function named step sequence and the next two lines are generate the step sequence. It creates a sequence of indices n from n1 to n2, then sets x to 1 where n is greater than or equal to n0 and 0 otherwise. This script demonstrates the shifting of step sequence towards the right and left using the step sequence function. It shifts the sequence by modifying the n naught argument accordingly. It also demonstrates the shifting of scaling the step sequence by multiplying it with a scalar value. And this graphs are plotted using the stem command. For the third task, we are required to generate a unit step function using the unit impulse function that we created in task 1. Firstly, we can see that whether we can create it or not. For this, we have taken n1 is equals to 5 and n2 as 5. Unit step sequence is zeros, 1, n, no, n2 minus n1 plus 1. This sets the range for unit step sequence n1 to n2 and initializes an array to store the unit step sequence. Here's the output. Now we will see whether we can shift this uh, step or not. For this, we have this function. This loop generates a shifted unit step sequence. This loop iterates over each value of k within the range n1 to n2. For each k, it generates a delta function that is shifted by k and adds it to the unit step function. The output of this function is we can see that we have shifted our unit step sequence from 0 to 1. The fourth task requires us to create different functions using the impulse sequence. We have defined the three signals that are provided to us for each sample k in the given signals. It generates a shifted impulse sequence using the impulse sequence function. It ensures that the generated impulse sequence and the current sample x of k have the same length by padding the zeros if necessary. It then scales the impulse sequence by the current sample value x of k. The scaled impulse sequence are summed up to reconstruct the signal. Inside the loop, it plots the reconstructed signal for each iteration. Each subplot shows the reconstructed signals corresponding to x1, x2, and x3 respectively. The plots are updated in each iteration to show the progress of reconstruction. It pauses for 1 second in each iteration to allow for the observation of each plot. Moving on to fifth task. The fifth task requires us to separate the even and odd parts of any given function. It checks if the input signal x has no imaginary component indicating that it is a real signal. If x has an imaginary component, it throws an error. It aligns the input signal x with respect to the index n. It ensures that the signal X and the index N have the same starting point. This alignment is necessary for further processing. It decomposes the aligned signal X into its even and odd parts. The even part is computed as the sum of the original signal and its time reversed version divided by 2. The odd part is computed as the difference between the original signal and its time reversed version divided by 2. Now we have the example usage for this function. Here's the output. In the last task, in the last task, we are required to sample a given continuous time sequence, where t is a time vector ranging from 0 to 2 seconds with a step size of 0.005 seconds. F represents the frequency of the continuous time signal. Fs is the sampling frequency, and we have verified the Nyquist criteria. Ts is a time vector representing the sampling instance ranging from 0 to 2 seconds with a step size of zero point 0.1 seconds. It generates a continuous time cosine signal. It creates a It generates a continuous time cosine signal using the formula cos f into 2 pi into t. It creates a subplot and plots a continuous time signal using the plot function. It generates a sample signal y by sampling the continuous time signal at the specified sampling instance. The sampled signal is represented by red stamps with circular markers. Access labels and titles are added to both subplots to provide context for the plots. Here's the output of the code. Thank you so much for watching.